So we have 3 presentations more, and the next is by Samuel Brown, who is at the Department of Polymers and Coatings, and he will make another presentation on metal nanoclusters and their optical properties.
Yes.
Floor is yours.
Thanks, Dimitri. As you mentioned, I'll be exploring the oxidation states for optically active silver nanoclusters. So to begin with, I'm just going to describe silver at different length scales. So here you can see we have silver in the bulk, just a silver metal block. And then this, if you look, is a TEM image of a silver nanoparticle that's about 6 nanometers in diameter. And then here's the model that we'll be working with later, a silver nanocluster that's only 13 atoms total. And then here's the representative density of states for each one of these models. So just kind of for reference of what we'll be looking at. So because the density of states becomes discretized for the smaller nanocrystals, that allows for different optical transitions. And then work by Diaz and Ross show that, one of the papers showed that you can actually get fluorescence from these models. And then with the nanoparticles that are slightly bigger, you can get surface plasmon resonance, which alters the absorbance properties. In this presentation, though, we'll be focusing mainly on the silver nano clusters, the very small ones, that can be optically active. So here's a molecular dynamics room temperature of the model that we'll be going over. So it's a silver nanocluster with 13 atoms making up the core of the silver, and then it's passivated with 12 cytosine molecules. So typically when they synthesize these in the lab, they use DNA as a scaffolding material. So for this case, we're using cytosine as the representative scaffolding.
May I interrupt you right away?
Yeah.
Do you know the structure? Is it known experimentally that it's really setting atoms in the silver? And also what the conformation silver has? Is it experimentally known, or you just took this structure because you need some to
I think
start?
something just to start with.
Okay, so no experimental data on this.
Yeah.
Okay.
So what we wanted to do first was just explore the different oxidation states and charges of the system to see if we can find a lowest energy. And when we did that, we found that the lowest energy was at a charge about negative 500, which is extremely low. So we decided to kind of explore different areas. So we went and looked at the charges around the neutral state. And looking at this, we can see that we get a deviation from the parabolic function we saw earlier to a quadratic function here with a inflection point around -6. This inflection point doesn't give us a whole lot. I looked at density states around it, and it seems to be similar. But looking at these models, we then explored the band gap for these ones, which is here. So I didn't mention we looked at different spins of 0, 1, 2, and 3. So this is spin 0, 1, 2, and 3. And then we looked at the band gap for all these different oxidation states. And for high oxidation states from about 3 to 10 in these models, we can see that the band gap considerably widens to about 2 eV. And since we did this for both alpha and beta electrons, we multiplied the band gap of the beta electrons by -1, so that's why we have a negative band gap here. Looking at the models that were optically active and had a band gap in the previous one, we then we plotted the band gap, the HOMO-LUMO energy for these different states, which is here. So you can see for a higher oxidation states, +11 compared to +5, that both the HOMO and LUMO energy drop, and that's pretty much independent of the spin of the system. So for now, we're just going to look, in the interest of time, at these two different spin states, the optically active systems where both the alpha and beta electrons both have band gaps. So looking at the density states of these systems, you can see that, as we'd expect, all the electrons are within the conduction or the valence band, and where if you excited it, they would jump into the conduction band, and you'd expect to see some sort of fluorescence or something like that. And then if you increase the charge, so you're increasing or decreasing the number of electrons, you lose states. So that's why it looks like it's more discretized in these cases. So we're now going to look at some of the optical properties, absorbance, and some of the different molecular orbitals for just this specific model. So looking at this, we determined the oscillator strengths for that, and using this equation here, we can develop an absorption spectra using these oscillator strengths, which is what we have here. And these vertical lines indicate the 4 strongest oscillator strengths, so the 4 most probable transitions, which are also listed here. So looking at these the molecular orbitals of these 4 strongest transitions, we see that for all the lower energy states, so this is where the electron would first preside before it is excited, that all molecular orbital resides right around the core of the silver. But then when we excite it, it jumps to a molecular orbital that resides predominantly on the ligand. So this kind of gives us an idea that not only is the size of these silver nanoclusters and the charge important to the photophysical properties, but the ligand itself is also plays a role in the fluorescence. So just a quick conclusion. We have a silver nanoparticle. We looked at the different energy, and we found the minimum to be around -500. But then we looked further near neutral states. We saw that several of these would have a band gap open up, and then we looked at it and found that the ligand played a critical role in the fluorescence. So,
let's thank Sam for